Hi students, and welcome back to our combination chapter 7 and 8 on types of bonds and characteristics of those bonds. So what we looked at when we left off, and it was a while ago, so I just want to take a second, is we looked at how the difference in electronegativity was able to tell us if the type of bond that had formed was ionic, polar covalent, or non-polar covalent, and that we took the two electronegativities and we subtracted them, and then based on where they fell on the number line, that would tell us what type of bond was going to be formed. Now that we know what kind of bond is going to be formed, we're going to spend some time looking at the characteristics of these bonds and what we can expect once an element has formed that kind of a bond. So we're going to start out with our covalent bonds, and we're going to focus on those for a little bit. Remember that in a covalent bond, atoms are what we say shared. And remember that that's not really shared, right? That's like a knockdown, drag out, fight to the death to try to win that electron away from the other atom. In a covalent bond, both atoms are quite convinced that they will be completely happy if they are able to steal an electron from their neighbor. They reach over to steal that electron from their neighbor, they start tugging it back toward themselves, and that's what ends up being this share of a covalent bond. Remember that the share can be even, which is like they're evenly matched. So imagine you in a tug of war against you. You're pulling evenly and then you're pulling evenly back and you're stuck there. There's not going to be any progress. Or it can be an uneven share, a polar covalent bond, in which case the difference in electronegativities is big enough that the electrons are not even in the center, but it's not so big that either one could win and actually pull that electron away. So the electrons, although they're to one side, they're not actually taken. So what we're going to be doing now is working on how we could represent these molecules, which are held together with covalent bonds, how we can represent these molecules on paper in a way that tells us a little bit about how they're behaving. One really important thing that we need to do as chemists is be able to predict the behavior of a molecule. And the first step in being able to predict that behavior is being able to draw the molecule and understand how it is sharing evenly or not sharing evenly the electrons within the molecule. So we're going to start this process by drawing the valence electrons on individual atoms. And then we'll kind of work our way up to fitting them together like puzzle pieces into molecules. When we draw an atom or a molecule, we want the drawing to be simple and to be clear and to have only the information that we really need. So to that end, we are going to draw our molecules showing only their valence electrons. We're not going to bother with drawing the kernel or the interior electrons because they don't determine how the atom behaves. What determines how the atom behaves is its valence shell. So we're only going to be drawing the valence shell when we draw the electrons to show how bonds are forming. In chapter 4, we learned how to draw an electron configuration like this one that we see here on the slide. And so this is the electron configuration for fluorine, and so it has 1s2, 2s2, and then 2p, and it has 5 electrons in its outermost shell. So one of the things that we talked about in chapter 4, but you may or may not remember, is that the valence shell is that highest number of possible energy level. And so when you look at this, you're going to see that there are 2 in the S, and then there are 5 in the P, and so all together we have 7 valence electrons in fluorine's valence shell. It wants 8, don't forget that, octet rule, but it has 7. We can tell an atom's valence shell, or how many electrons it has in its valence. This is my representation of the periodic table, and remember that these are the S, the P, the D, and the F blocks on the periodic table. The valence shell consists of just the S and the P block. So only S and P contribute to the valence shell. So we're going to look at the S and P block. If the atom is in the S block, its valence number is its group number. So everything in group 1 has 1 and everything in group 2 has 2. If the atom is in the P block, it's the group number minus 10. So if it is in group 13, it would have 3 valence electrons. So everything in group 13 is going to have 3 valence electrons. And everything in group 14 is going to have 4, and so on. 15 has 5, 16 has 6, 17 has 7, and 18, those are the noble gases. Remember, they have the full 8. So fluorine, if you'll notice, is right here, and we just said fluorine has 7 valence electrons, and I can also see that by looking at it on the periodic table and see that fluorine has 7 valence electrons. So instead of this very complicated, all these arrows and all of this stuff kind of drawing, we're going to be trying to focus on just showing what matters, which is the valence shell. So if we look at fluorine here, we are seeing a different way to represent 1, 2, 3, 4, 5, 6, 7. So we are able to represent fluorine with its 7 valence electrons by just simply putting them in the circle around fluorine. And we're going to take that even one step farther as we create what we call a Lewis structure for fluorine. So a Lewis structure is done to show how atoms are related to one another and how their valence electrons are interacting with one another. So I've left a reminder up here about how we know how many electrons are in the valence shell. If they are in the S block, it is their group number. If they're in the P block, it's the group number minus 10 to tell us how many electrons are in the valence shell. So when we start a Lewis structure, we start by drawing just the individual atom. So we start by recognizing the number of valence electrons and putting them around the symbol for the atom. So let's start by drawing the Lewis structure for fluorine. If I start with fluorine, fluorine is represented by the symbol F. And we've already established that fluorine has 7 valence electrons. And so what we're going to do is we're going to imagine fluorine in a box. Okay, and we are going to fill fluorine up with electrons, 1 per side and then 2 per side, just like we do with the arrows in our electron configuration, where we put 1 in each and then 2 in each. Okay, so we're going to start like that. So for fluorine, I'm going to do 7. So I go 1, 2, 3, 4, and then there's 1 on each side, but I still have more to do. So I pair them up. 5, 6, 7. So the dot structure, or the Lewis structure for fluorine, is an F in the center with 7 dots around the outside. Officially, there's no box. Okay, we don't actually put them in the box. We just imagine the box. And these little underlines can be kind of like the underlines of the S and the P block. Okay, you can think of them like that. We have 4 here, 1, 2, 3, 4, and we have 4 here, 1, 2, 3, 4. And we kind of apply the same rules where we put 1 in each and then 2 in each as we go around. So we're going to do a whole bunch more. Okay, so we're going to just do the Lewis structures for each of these. The first thing we need to do is we need to look up the number of valence electrons they have. So for sodium, sodium has 1 valence electrons. So for sodium, we're going to put just a single dot with sodium. An important thing to know here is that there makes no difference where the dot goes. Sodium, the dot can be on any side, just so long as there's only 1 dot on one side. Carbon has 4 valence electrons. If you go look up carbon, it's in group 14. 14 minus 10 gives us 4 valence electrons. So we would fill this one by putting 1, 2, 3, 4. Now each of my sides are full, but I'm also done filling in electrons, so I don't need to go back around again. Oxygen is in group 16. So oxygen has 6 valence electrons. 1, 2, 3, 4. 4, and then I keep going, 5, 6. And the last one on my list here is aluminum. Aluminum is in group 13, which means it has 3 valence electrons. And so we'll put 1, 2, 3 dots around aluminum. Now the next piece of this is that each of these is like a little puzzle piece. Anywhere they have a double dot, we call this a lone pair. And lone pairs, even though they sound like they're alone, lone pairs are happy. We don't do anything with lone pairs. But the single electrons, these ones, need bonds. So what we know about oxygen, just from looking at this, is oxygen wants 2 bonds. Just from looking at carbon, we can see that carbon wants 4 bonds because it has 1, 2, 3, 4 unpaired electrons. And aluminum, you might propose, we'll come back to aluminum because really it's going to try to lose those electrons, but you might propose that aluminum would want 3 bonds. It's not a bad guess. It's not exactly how it works, but it's not a bad guess. So we can tell by looking at these unpaired electrons how many electrons an atom would want to lose or how many it needs to bond in order to be happy, in order to get its stable octet. So this is a good way to predict how an atom will behave. When we put these together into molecules, we can represent these dots, these shared pairs, we can represent as 2 dots, or we can represent them as a dashed line. So here we have a Lewis structure, and this is what we're going to be working on creating in just a moment, where we start with the Lewis structure for chlorine and the Lewis structure for phosphorus, and we start to fit our missing or unpaired pieces together like little puzzle pieces, and we start to find a match for them. And as we find a match for them, that is going to fill the octet or the outermost electrons for those particular atoms, leaving them happy, fulfilled, and acting like a noble gas. So we're going to be looking at that behavior. So I'd like to start us out by looking at this actual example, which we would call PCl3. So the P means phosphorus. Typically, the element that comes first in the name, or carbon, is going to be the center of the molecule. It's also typically the more electronegative atom that will be the central molecule. So those are 3 ways that you can choose. You can decide to use the one that comes first, or the more electronegative, or if carbon is a choice, then carbon tends to be the central atom. So we start with phosphorus, and phosphorus is in group 15, so it has 5 valence electrons. So we put them on. 1, 2, 3, 4, 5. So how many bonds does phosphorus want? 1, 2, 3. It wants 3 bonds, which is super lucky because we have 3 chlorines, which helps us to kind of get the feel that we're going to be matching 1 chlorine to each phosphorus. So let's go ahead and draw a chlorine atom. I'll put him over here to begin with. And chlorine has 7 valence electrons. If you look up chlorine, it is a halogen just under fluorine in group 17. So we're going to put 7 valence electrons around chlorine. 1, 2, 3, 4, 5, 6, 7. Now you'll see some people do this as X's and dots, or one color and another color. My experience for you guys is that for the most part, you guys just draw dots anyway, so I'm just going to leave them as dots. When I see this unpaired electron and this unpaired electron, I want to connect those. So now I've just created a bond. So my bond is shown as this dash connecting the 2 atoms. So this is phosphorus and 1 chlorine, but I want to see phosphorus and 3 chlorine, so I rinse and repeat. I do the same thing over. So I'm going to put chlorine down here now. You could, and I hope you will someday, put the valence electrons now around chlorine in such a way that it will easily bond with phosphorus. See me putting my unpaired electron there again, and I can go ahead and make this bond. But sometimes you won't see it coming. You'll make a mistake. And so you'll do something like you'll put chlorine here, and you'll say 1, 2, 3, 4, 5, 6, 7. And you'll go, oh shoot, I want these two to connect. It's messy. It's not how we like it, but it works. Okay, it shows me the connection between them. But if you can, try to rearrange or shift the electrons around so that they match up directly and are able to pair into their bonds. So this is how we would draw PCl3, and now we're going to try practicing to draw a few other ones together. So first, I'd like you guys to start by drawing N, F, C, and Cl with the appropriate valence electrons around them. Okay, so I started with the individual puzzle pieces up here, N, F, Cl, and C. So now it's pretty easy to start fitting them together to form molecules. So the first one we're going to look at is NF3. So I'm going to have one of these, one nitrogen, and then I'm going to need to plug in 3 fluorines. And what we can see is nitrogen wants 3 bonds, right? It has 3, 1, 2, 3 unpaired electrons, and fluorine only has 1 unpaired electron. So I hope that you can see that we're going to try to plug this 1 unpaired electron into each of the 3 sides of nitrogen. So I would put my fluorine over here, and I start working my way around, and I want my unpaired electrons to face each other so that I can make a connection between them. So continue on. Next fluorine comes down here. 1, 2, 3, 4, 5, 6, and I want that unpaired one to connect. And then over here, 1, 2, 3, 4, 5, 6, and 7 unpaired electrons to connect. Before we move on, I want to show you how you can check to make sure that you've done this correctly. If I count around the outside of nitrogen, I should now find 8 valence electrons. So count with me. 1, 2, 3, 4, 5, 6, 7, 8. And the same thing should be true for each of my fluorines. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 electrons around each element. I have 1 nitrogen and 3 fluorines. N, F, 3. Perfectly done. Okay, so let's move on to CCl4. Okay, so we start with carbon. Remember, the one that comes first, or carbon, if we have the choice, is going to be the one in the center. And so carbon is in group 14. It has 4 valence electrons, so I'm going to put 1 on each side. And now, kind of the same concept, because chlorine is another halogen. It looks very similar to fluorine. We're going to put 1 chlorine on each side with its unpaired electron pointing towards carbon. So we start over here and we do chlorine, 1, 2, 3, 4, 5, 6, 7, and connect. Chlorine, 1, 2, 3, 4, 5, 6, 7, and connect. Chlorine, 1, 2, 3, 4, 5, 6, 7, connect. And up here, chlorine, 1, 2, 3, 4, 5, 6, 7, and connect. You can imagine, and you're right, that when we do a test on this, you will be writing these out on paper and sending pictures of them to me in order to be graded. So it's important that you're learning to draw these out for yourself, okay? So the last one I want to try together is HF. And before we do that, let's just count up and see that carbon ends up with 2, 4, 6, 8 valence electrons, and chlorine 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody has 8, all full octets, all full valence shells, all happy, happy elements. And so now we've these 2 molecules. Now let's look at HF. So we start out with a fluorine, and now I want to add a hydrogen on. So I'm going to put hydrogen here, and I'm going to go look up hydrogen on the periodic table, and I'm going to find that hydrogen is in group 1, which tells me that it only has 1 valence electron. So I'm going to put it right here and make my bond. And I have made fluorine happy with 8 valence electrons, but hydrogen does not have 8 valence electrons. So in this example, we have found an element that does not have a full octet. And it turns out that hydrogen is one of a handful of elements on the periodic table that cannot and will not achieve a stable octet through any type of bonding. It just doesn't have enough electrons to pair up to end up with 8. So let's look at what is happening with hydrogen, and we'll start by looking at HC. So once again, chlorine is a halogen, so it has 7 valence electrons, group 17. And when we plug in hydrogen into a bond with chlorine, we get this bond here with them. And what we see is that once again, chlorine has 8 valence electrons, but hydrogen only has 2 valence electrons. So hydrogen has not achieved a stable octet. There are a list of 5 elements that are unable to achieve a full octet no matter what. Hydrogen, helium, lithium, beryllium, and boron. They're the early elements because they don't even have a kernel with a stable octet. So these elements cannot achieve a stable octet, and most of them are going to try to do this. We call this, as we mentioned before, a full duet. Okay? So some of them can form a full duet, some of them can't even do that, and that's okay. We just sort of let them be. They do what they can to get as stable as they can, even if they can't quite make the original goal of 8 or 2.